Hi guys. Today what we're going to be doing is completing Investigation 13, and really what Investigation 13 does is put Le Chatelier's principle into action. We're going to be looking at 6 different systems at equilibrium and applying different stresses to see how the equilibrium responds as a result of those stresses. The first system that we're going to look at is an acid-base indicator equilibrium, and it involves the acid-base indicator bromethymol blue, which I have the chemical formula here written on my whiteboard. So all acid-base indicators are relatively large organic molecules, and they change color as a result of changing pH. In this case, what we're going to be doing is stressing an equilibrium system that exists between the acid form of bromethymol blue and the base form of bromethymol blue. And what we're going to be doing is either adding acid, adding base, or adding spectator ions in the form of sodium ions and chloride ions to see how these equilibriums will shift. For each of these equilibriums, I've written a K expression so that we can clearly start to see and think about how the addition of acid will cause this reaction to shift and result in a color change, and how the addition of a base will cause this reaction to shift and create a different color change. So here I have a solution of bromethymol blue, and I'm going to add some to my test tube. Okay. All right, so as you can see, it's just a light blue, transparent solution. The first thing that I'm going to do is add acid. I want you to take a moment and think about how increasing the concentration of acid is going to change this equilibrium. Alright, so I'm going to add acid, 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 acid. And as you can see, the equilibrium shifted, and now my solution is yellow because I have the acid form of the indicator. Now that I have the acid form of the indicator, I'm going to add base. And as I add base, you can see that my equilibrium is shifting away. All right, it's still a little bit yellow, but if I continue to add base here, I get it to shift back to blue. Okay. In my last test, I'll add the spectator ions. Note that spectator is the operable term here. As I add excess table salt to this solution, I can even mix it, but I will see no change. And I will see no change because neither of those ions, sodium nor chloride, are a part of my equilibrium expression. Now what we're going to do is look at a series of complex ion equilibria. In the first situation, we're looking at an equilibrium that exists between iron 3 plus ions, thiocyanate ions, and then this complex ion here between iron 3 plus and thiocyanate. Okay? I have a solution that's in equilibrium here, and I'm going to set up 4 different scenarios. And in each scenario, I'm going to add a different substance in order to try to stress that equilibrium. I'll add a solution of potassium nitrate. Note that both potassium ions and nitrate ions are spectator ions. That should give us a clue. I'm going to add iron 3 plus ions in the form of iron 3 chloride. I'm going to add thiocyanate ions in the form of KSCN, potassium thiocyanate. And then I'm going to add sodium hydrogen phosphate. Sodium hydrogen phosphate is going to form a precipitate with iron 3+ ions. So having given you all that information, hopefully you can start to think about how these stresses will impact the equilibrium and in which way the equilibrium can shift. All right, so to just give you some background, these ions in solution have a reddish orange color. They're transparent. These have, they're relatively colorless, and then obviously this complex ion is what gives us the red color. All right, so here we go. First I'll add some potassium nitrate. Again, what I'm doing here is adding spectator ions. Okay. Can you see it? Yes, you can. Okay. And as I add these, what you can see is that no change is occurring here. There's no change occurring because these are spectator ions and they are not a part of our equilibrium expression. Next, what I'm going to do is add solid crystals of iron 3+ ions. So let's see here. It's in the form of iron 3 chloride, but really any iron compound will do. Let me get some of these out here. Oh, not too much. Too much. Okay. So I don't know if you can see this. Oh, whoopsies. All right, so here's an example of a crystal. And I'm going to add it, oh man, to my test tube. And you can already start to see the change at the bottom, but I'll add more. And then I'll mix it. Let's see, let's add a big one. There we go. And as you can see, what I've done is I've shifted the equilibrium to the right to make more of this blood red precipitate. All right. Now I'm going to add the thiocyanate ion in the form of solid potassium thiocyanate. This chemical is pretty old. I don't know if it's going to have as good as an effect. All right, but you can see that these are colorless and transparent crystals. And let's see if I can do this. All right. Okay. I'll try to dissolve this. And you can see that the color is changing. It's darker. Okay, so what we have here is a shift again to the right in the production of this complex ion. Okay. Lastly, I'm going to be adding crystals of sodium hydrogen phosphate. So remember, sodium hydrogen phosphate, or more specifically the phosphate anion, is going to form a precipitate with these iron 3+ ions. In other words, it's going to start to pull it out of solution. Think about how the equilibrium will shift. I'll add my crystals, and I'll give it a mix, and we'll see what happens. Did I hit record? You can already start to see at the bottom of my flask that it was changing color, and now it's completely gone in the opposite direction. because I've drawn these iron ions out of solution, and now I just have this transparent thiocyanate ion. Okay? I mean, it's hard to see. There is a pale yellow color, which indicates the presence of some of these ions as this is getting, as they are being produced, but as they are being produced, they're being pulled out of solution in the form of this solid iron 3 phosphate. In this complex ion equilibria, what we're looking at is the equilibrium between copper 2 plus ions and ammonia, and then the complex ion that forms between the two. The complex ion that forms between the two is a very deep blue color. So to just give you a little bit more information as I proceed with this, we're going to start with a solution of copper ions. To those copper ions, I'm going to be adding a base, ammonia. As I add that base, it's going to react with the water that's in solution to form hydroxide ions, and initially I'm going to form a light blue solid. That is the copper 2 hydroxide ion, or solid, sorry, insoluble salt. But as I continue to add ammonia, this will get replaced for the more favorable here, because of the large concentration of ammonia that I'll be adding, complex ion. So I'm going to start by forming this complex ion. Then I'm going to add different stresses. I'm going to add hydrochloric acid. Hydrochloric acid is going to pull these ammonium ions out of solution. Ammonia ions out of solution. And it's going to drive this to the left. And then obviously I can reestablish this complex ion by adding more of my concentrated ammonia. So let's get started here. Okay. So again, concentrated ammonia. I'm going to add. You can see that I have light blue and I have dark blue. I think I've actually added too much to start with for my, I'm going to need a larger test tube, so hold on for 1 second. You can see right now I have my copper 2 hydroxide forming. Okay. I'm going to continue adding my concentrated ammonia. So I'm adding, I want to add an excess, so I'm going to keep adding this. And you can see that as I add it, I am getting the formation of the complex ion, but it needs to be in excess. It's almost there. But I want it to get to the deep blue color that it's supposed to be. Okay, it's really pretty to look at. Okay, here we go. All right, so I've established the formation of my complex ion, and now what I'm going to do is add acid. That acid is going to pull the ammonia ions, or the ammonia out of the complex ion and drive the equilibrium back. So you can see I have my copper 2 hydroxide again. And if I keep going, I'm going to end up where I started. Okay. Here we go. Back where I started. All right, so obviously this is a little bit more dilute, so the blue color is not exactly the same as it originally was. But hopefully you were able to see how the addition of these two substances stress the equilibrium and how the equilibrium responded as a result. In the next complex ion equilibria, I form the complex ion between copper 2 plus and water. When I take the solid copper 2 chloride and I dissolve it in water, what I get is an equilibrium system. Okay? I have the formation of this complex ion here. What I'm going to be looking at today is this system. I have started, or I will start with the solution here of this complex ion and aqueous chloride ions. And to this system, I'm going to add stresses. I'm going to add water. Water is going to replace, or I'm sorry, I'm going to add chloride ions. The chloride ions in excess are going to drive the water out to form a new complex ion between copper 2 plus and chlorine. Then I'm going to add water, and although water is not a part of our equilibrium system, the water, when in excess concentration, will replace the chlorine ions in this complex ion and come back to the complex ion between copper and water. Here I have my solution of copper 2 chloride in water. I have my complex ion formed. Okay. As I said, I'm going to start by adding concentrated hydrochloric acid. That'll be my source of chlorine ions. Let's see, can you see? And you can see as I add, the solution is changing color from blue to green. Chlorine is replacing water and forming a new complex ion. I think I can even add a little bit more, although that just means I'm going to have to add a lot of water to drive it back. Okay. Okay, so I have the green solution. Now I'm going to add excess water and shift my equilibrium in the opposite direction. Continue, you can start to see the solution is going from green back to blue. Continue, and now you can see it's changed. It's back to blue. Okay. All right, we're going to look at another equilibrium involving a complex ion, and this complex ion is one that involves cobalt. So right now what I have a solution of is this complex ion here. Okay. What I'm going to be doing is stressing this. In stressing this system, I'm going to be adding excess chlorine ions in the form of solid sodium chloride. You can see how that may stress this system. Note that when this is in excess, I get a different complex ion between cobalt and chlorine. I'm going to add acetone. Acetone removes water, so you can see what would happen as we remove water from here in the presence of chlorine ions. When I have this complex ion, I'll be adding water, so you can see that in the presence of excess water, water might replace the chloride ions in this complex ion. I'm going to add silver nitrate. Silver nitrate is going to precipitate any chloride ions that I have. So you'll see that it may pull the chlorine ions out of this complex ion to get the formation of another complex ion, or complex ion with water. And then energy is a part of this diagram. Okay, so here, if it's hot, you can see that it might shift in one direction to consume energy, and if it's cold, it might shift in another direction to produce energy. So, I don't know. Let's see what we can do here. Add some. Okay. To start, I'll go ahead and I will add sodium chloride. And as you can see, the blue color just intensifies. Oopsies. As I have my complex ion between cobalt and chlorine. Now what I'd like to do is add water. Of course, I'm going to have to rinse some of this down first. Okay, but note that in the presence of water here, I have a different complex ion. This is excess table salt here, but now I have this complex ion that is pink in color. So now what I'd like to do is add some acetone, see if maybe I can drive it in the other direction. All right, so remember, acetone is removing the water. And when it removes the water, I get the formation of the blue complex ion. Okay, there's still too much table salt though, but you can see what's happening. I think what I'm going to do is shift this over now to here. Okay. See if maybe, actually I'm going to remove some of this. See if now I can get this to be blue. There we go. Okay. Now what I'm going to do here, excuse you, is put this down. Okay. And I am going to take this. Okay. And I'm going to add silver nitrate. Remember, silver nitrate precipitates out the chlorine ions. I would thought that it would have turned blue, but now I have a lot of pink solid. To think about this in more detail. I wonder what's happening. Okay. Okay. Maybe there's just too much chlorine and not enough silver chloride to pull it out of solution. Okay. Now what I'd like to do is experiment with temperature. Okay. So if I add heat to this system, it should shift to the right in order to offset that change. That would favor the formation of the blue complex ion. I have warm water here, and we can try to see what might happen. And I think we can see that it is starting to go from pink to blue. All right, so I'm going to leave this in here a little bit longer, but you can clearly see the color is changing. At least I hope you can clearly see it, because I can. Okay. So you can see now there's blue If I change it and I put it in cold water, we give it some time, what should happen is that you see the blue color start to fade and it go back to pink. Okay. All right. I think the last change that I should try is to add water, excess water. So I'll take a small amount and I'll add excess water. And you can see excess water causes it to go from blue to pink, from one complex ion to another.